Hello guys, now I'll be giving my second part of the seismic reflection survey, data acquisition and the concept of the filtering. Along with that, we'll be discussing about the different kinds of filtering techniques like digital filtering, Fourier transformation, convolution, deconvolution, and along with that the most important thing of seismic data processing will be how to deal with the velocity, proper velocity, what is the common midpoint gather, how do you stack the trace, what are the noise, that means multiple, that comes in the seismic data, and how to eliminate that we will be discussing as a in our lecture. I think before going through this lecture, it's my request to all you please follow my first lecture of this basic seismic traverses travel time of the reflection curve, which will help you to know to understand more about this lecture. So it is also an important topic for the combined UPSC geoscientist exam. Seismic data acquisition, you can have the data acquisition technique like source and receiver combination, which is very close to each other. It is called a normal incidence section. Almost one source, the shot is triggered and it will be received in the receiver number 1 or geophone. For land the receivers are geophone, and for marine it is called the hydrophone. For each shot that there is a traces which is plotted along with the time. This is the very basics. Generally, geophones are designed in such a way that they enhance the vertical motion, that is called reflected compressional wave. So normally there is a combination of geophones are there that will, eliminate the noise. So there from source, the shot is triggered and that will be reflected, and there is a reflected P wave, reflected S wave and the direct P wave. Generally this S wave and the direct P wave records the horizontal particle motion, and in the geophone it is having a little response, but in the reflected P wave it is having a vertical motion which is having strong response in the hydrophone. So we deal with the reflected P waves that is coming. Generally in my last lecture I have also discussed about what type of minimum source pulse, maximum source, what type of sources are generally used. Still I am discussing. So there are impulsive source and the non-impulsive source. For the impulsive source, that is like a direct delta function and produces very sharp minimum phase wave of short duration. Generally we use in the seismic reflection surveying. For explosive type source we use dynamite, air gun, the thumper truck or the sparker for very shallow seismic survey. For implosive type we use generally water gun, steam gun in electromagnetic pulse energy source. For non-impulsive, the marine vibrator is used. So most commonly used in the marine survey is the air gun, and in land the dynamite is used, and alternative to that thumper truck is generally used. So our objective is to do the subsurface imaging with the seismic data. So generally when it shot is triggered, we'll have a pulse. And suppose we record the pulse at a device number 1 or the instrument at 0.4 second. And for there is an offset, means a certain distance between the receiver source and the receiver. So due to which for the device 2 there is another shot, there is a delay in time, and that records a reflection at 0.8 second. So we can have in subsurface imaging many shots and many devices that is arranged in land, either land or in the offshores. For marine survey, how we can depict the shots? There is a ship is going, suppose there is a source in the ship, suppose the air gun is used from a single source. Suppose the shots are generally fired and we can have a response at all the from one shot all the receivers. Generally this method is called shot gather. From one shot we will have response to all receivers, 1 2 3 4, and based on the offset there is a arrangement of shots. It is called reflection hyperbola. For direct arrival the slope is much steeper than the reflection curve. That travel time curve of the direct arrival and the reflection I have already discussed in my previous lecture. Now for each shot, you can see the reflections are recorded in the 5 receivers, and there are 5 bounce back point along the interface 3. So we are just imaging the subsurface 3 in the seismic method. Now, in seismic survey, although we do for shot gather to enhance the signal to noise ratio, the common midpoint gather is very much of important. So the collection of which is the main task of the seismic image processing. You will see that the seismic traces are being, gathered at a common point between the source and the detector. The common point that point is called common depth point or common midpoint. When our subsurface is not purely horizontal like this, there is some dipping is there. There is a problem. Means the shots. The stacking is not proper, and the in dipping reflector, the no longer the reflection points. The lies direct between the source and the detector. So there is an offset here. So that disturbs our stacking process. Now, to illustrate deep in a very detailed way about the common midpoint method, the ray path diagrams are displayed in the left. So from one shot, the three are shot gather. From one shot, the ray is received in receiver one, and the point, the seismic trace have a common point between the source and the receiver. Here, the seismic trace have a point between the source S2 and the receiver R3. And for this shot number 3, the seismic trace have a common point between the source S3 and the receiver F5. So combining all these three, we can tell that the for seismic trace lies directly beneath the source and the receiver for S2R5, S1R1 and S3R5. This point is called common depth point at a distance, at a vertical distance h below the seabed or any land point. Now the travel time curve with no reflection, this represents a hyperbola which is commonly described as using this equation. So you see there is a traces that are arranged in such a way that the stacking is not possible. So in order to do stacking, we need to carry out a correction that is called NMO correction. This is nothing but subtracting this travel time value from the time two-way time, and using that we can have the traces that will be that will be arranged at a single horizontal line. In my next slide, I am going. Generally, for a sequence of horizontal reflector, there is a through multi-layered ground. There will be refraction at the layer boundaries, and we know the time distance curve generally follows such a rectangular hyperbola path. And it is notable that with the offset increasing, for the hyperbolic time curve, the divergence also increases. Vrms is the velocity of the layer to the nth interface. Generally, this equation is updated with the velocity v with the vrms. So how do you define the rms velocity? So we take for every layer we do square of the velocity and multiply with the respective time of the ray through this layer, and we take a sum and divide by the total time and take a total root over of that equation, and we will get the RMS velocity, and from that RMS velocity we will the travel time hyperbolic curve. So just I was telling about how for a reflection curve there's a traces are arranged in such a way that they are not in a single line. So to do that we'll have to do NMO correction. So after NMO corrected, uh, TF minus T0, all the seismic traces come to a single line. And when you stack these traces, will signal by noise ratio is greatly improved and we'll have a single trace. So our main objective for the seismic processing will be to have a trace that is have least signal to noise ratio, and that will be coming from CMP gather. So this is our pictorial depiction of the normal move out correction in all the seismic processing technique. will be doing this method in a software using this technique. And it is also notable that the curvature of this hyperbola is a function of the average velocity down to the depth of the reflection. So it is depends on the velocity of that layer. So like that, when we're having the stresses that are little down, the curves are down, you can see the trend, the velocity we can say it is little slow. When the correct velocity is there, the traces will be exactly flat. And for velocities too much fast, the curves will be up. The trend of the curves will be upward. And we can say the velocity is fast. So our objective will be to have a flat velocity gather using the processing technique. Then we'll have proper subsurface imaging. Now, you know that the seismic ray that comes after reflection at a single interface is known the primary reflection. So apart from the primary reflection, there are many rays that comes to the surface after bouncing back. And for you can say for double path multiple, we'll have a double time of the ray, but their amplitude is low compared to the primary. There will be absorption and there will be loss of energy. So you can easily detect that through a seismic section. But there are many rays that have amplitudes that's comparable to the primary reflection because the rays are reflected at the interface of higher reflection coefficient. For the you can see this is a first order reflection, this is a second order multiple, and it will have longer travel time compared to the primary. So in a section we can easily detect it. But for water layer reverberation like that, there is a source is where that the ray that are detected at the seabed and then it comes received, that is have the amplitude compared to the primary. Also for the peg leg multiple, this is called peg leg multiple, it is little bit harder to detect in a section. So our objective will be to detect multiple, predict multiple, and to eliminate this from a section that are generally termed as the noise, what we don't need in our section. I'm discussing about what type of noise are there in the seismic reflection processing. Digital filtering. So we for it is our standard practice to consider the waveform as a combination of signal and the noise. The noise is classified under two components. There's a random noise and there is a coherent noise. And for digital filtering is widely employed to improve that signal to noise ratio in the geophysical, especially in the seismic data processing. So there are mainly two types of filters that there, frequency filter and the inverse filter. So noise is classified as a random noise and the coherent noise. Generally, random noise is the background vibration due to wind, rain, and other effects. Coherent noise is hard to detect, hard to eliminate, and it is a component of the waveform that is generated due to geophysical experiment. Suppose there is a for seismic source, the surface wave that travel to the detector and that can obscure the desired signal, that can be classified as the coherent noise. And depending upon the noise, it may be filtered out by identifying the particular characteristics of the noise and by designing a special filter. Now what type of, now for this is a very important topics to be discovered before proceeding for any filtering operation. So there is, for suppose we have a time series data ft in a frequency space using that transformation, very Fourier can have a go to the Fourier space, and we can also travel come back to the inverse Fourier space in a time domain using that equation f omega cos 2 pi omega t. Suppose for amplitude, in amplitude spectrum is the root mean square of the cosine square plus sine square integral. We can have that amplitude spectrum in a frequency space. So computationally it is very easier to do in the frequency space compared to the time space. For a 2D data distribution of gravity and magnetic also the we will go to the k space, means frequency space, using that equation where k are the wave numbers that will be frequently used afterwards to have a lower cutoff, higher cutoff, radians per ground unit, and the wave numbers are the special counterpart of the frequency. So k will be 2 pi by lambda x and ky will be 2 pi by lambda y. So the Fourier, based on the Fourier transformation, we can have low pass, band pass, directional filter, and there is also another kind of filter, convolution is also there. So we'll be the convolution theorem we will be going to discuss in our in next few one slide. Suppose in a convolution domain, function is like fxy, if this is star is the convolution function. So in the Fourier domain, if we multiply the corresponding Fourier transformation, we'll get that in total function. So for particular, based on the particular cutoff frequency, the low pass or high pass filter will pass the band. This is the condition to that. K greater than 2 pi by lambda c cutoff frequency, K less than 2 pi by lambda c for high pass filter. Now talking about the seismic signal, seismic wave processing, this is very important to discuss about the idea of sampling theorem or the aliasing. So that digital filtering is completely dependent upon it. So to do that, one basic thing to remember is that when you are sampling any wave, the sampling frequency must be greater than twice into highest frequency component. That is the Nyquist frequency, and this theorem is called Nyquist theorem. So by an example, we are going to illustrate that. Suppose we are sampling frequencies 250 Hz. So our first first wave is 75 Hz signal. So when a sampling frequency is 250 Hz, that is greater than twice into that 75 Hz. So all the frequencies are being sampled. That means 75 Hz. No problem in that. But for 150 Hz signal, 175 Hz signal, it yields the value same as 75 Hz because that is not that frequency 250 is not greater than twice into that frequency. So we'll have the sampling, it yields the values of 75 Hz by represented by a dotted line. And the next frequency is 250 Hz, which yields a completely straight line that can be that seems as a DC bias because that frequency is same as the sampling frequency. So we can't get any sampling values. It yields only the constant values. So this thing can be termed as aliasing. For different function, the Fourier transformation are depicted. For a spike function, this is called infinite bandwidth frequency spectrum. This is for DC bias, this is called a single spike function. For transient waveform, we will have a box function, and based upon the, within the transient waveform, the time pulse, the box function which is defined. It is directly in the time domain is inversely, inverse operation of the frequency domain. So shorter the time pulse, the greater will be the frequency bandwidth. The limiting case is that the Dirac delta function, where it will have infinite bandwidth of many frequencies. And this type of transient pulse are generally used in the seismic cases. So we can have like that we have discussed, there is a high pass, low pass, band pass filter, cosine filter. So based upon the particular cutoff value K0, the values below that cutoff frequencies, all the frequencies are passed. So we'll have a step function like that. For values greater than K0, all the frequencies are passed. So we'll have a step function like that. When we'll having K0 and K1 lower and higher cutoff frequency, we'll have a pass band in between that. And depending upon the direction, the inflection point and the degree of sharpness n, will have a filter response in like that. So due to the ringing effect associated, many times this type of filters are used with a band pass regime, generally for seismic cases, that is to eliminate the ringing effect in a seismic data. We'll move to the cases of correlation, auto and cross correlation. It's nothing but a measure of similarity between the two data sets. Suppose we will have a wave function 1, waveform 1, and there is a waveform 2, and there is some lag is there. So the cross correlation function, according to the equation of that for discrete data set and for continuous data set, will have a cross correlation that is maximum at the zero time lag and which reduce to a lower value at the large time shift. And now in my next slide, we'll be telling why we need cross correlation in a seismic data processing aspects. Before that, we'll discuss about autocorrelation. In just the signal y is replaced by the same signal xk. So it is this waveform that is cross correlated with itself. That is called the autocorrelation function. Okay, so if we have that lag is equal to 0, so the 0 time lag is called the energy because it is the square of the amplitude. It is symmetrical with respect to the 0 lag position. It contains all the amplitude information as it is evident from this equation, but none of the phase equation. Generally, for transient waveform, it decays to a large value, and for periodic waveform, it is periodic. These two cases are there. And by observing the nature of the autocorrelation function, we determine the detection of the hidden periodicities in a waveform. How is the waveform actually? For continuous function, the autocorrelation is defined by an equation like this. You can see for a zero time lag, it is the energy of the trace x tau squared d tau mod of x tau squared d tau. That is nothing but an energy. So, what is the application of cross and autocorrelation? As we already told, there is a two-wave form. This is a similar waveform you can detect. Autocorrelation function is a time lag, right and left. So it is symmetrical about the zero time lag. Now, what is this? This A and B defines. For A, the waveform is placed with lag tau. It is exhibiting a periodicity. Okay. For B is defined as an autocorrelation function with the side lobes. The side lobes with the spacing is defining the repetition period of the waveform, and that is now defining the this classify that is used to classify how is the waveform. That is the main thing of the autocorrelation function. So, but for cross correlation, we will having a waveform and the signal function. Now you can detect there is a hidden periodicities in the waveform. When the signal is waveform is autocorrelated, cross correlated with the signal function, it is used to define the hidden periodicities that like S1, S2, and S3 in a waveform that is concealed in a noise. So this is the application of the cross correlation, and this is the application of the autocorrelation. There are another more autocorrelation application is there to define the source wavelet. Now, like the autocorrelation and cross correlation, convolution is also another important operation. Suppose we have a input and there's a filtered output. So convolution is defined as that uh, input and convolution with impulse response of the filter. Pictorially, if we can say there is a spike input is there that is passed through a filter. As per the impulse response of the filter, the output is defined. The mathematical operation corresponding to the convolution is presented in that equation. That is, it is multiplied with ordinate wise and then shifting one position and summed. That is the basic definition of the convolution. So it is a commutative operation. Xt convolutive ft is equal to ftk. And what is this correlation with the cross correlation? So when we do cross correlation of phi xy, tau is equal to phi yx minus tau. So you can say using that equation that when we reverse the first data set and convert it, it is same as carrying out the cross correlation operation. So this is the similarity between cross correlation, relation of the cross correlation with the convolution operation. For a continuous function, it can be defined as the integration of x tau f of t minus tau. You can remember the the cross correlation is f of tau minus t. That is reversing the data set only. Now, this operation is very much important in the seismic data processing. I'll be giving an introduction only this. In my next lecture, I may be perhaps giving the detailed application and the details of the deconvolution operation. So generally, it is the process of removing the effect of some filtering operation. If we know the output seismogram, the recovery of the input wavelet represents the deconvolution operation. So how do we define xt? Xt is equal to yt convolved with the operation of f prime t. Suppose f prime t, we can say 1 by ft, it might be there. So if we just replace the substitute yt from that equation, you can say xt into ft into f prime t. And we already know that xt is multiplied with Dirac delta function. It will unit response, it will produce the same output. So this between 2 and 3 we can tell ft and f prime t is a delta t. So if we know the impulse response, that can be derived to recover the input signal xt. So geologically, how do we define the convolution with the reflectivity function? Generally, the seismic trace is formed as the convolved output of the reflected function with an input pulse. So let me show you. There is a geological function is there. So different elements might be there. There are different composition of the geological composition. Based on that composition, the acoustic impedance log is defined, and, and that accordingly the reflection coefficient that I have already discussed in my previous lecture, plus positive, negative, and along with the amplitude. Now, if we convert the reflectivity function along with the input pulse, we'll be getting a resultant seismic trace. So we already only know about the seismic trace. We don't have any information of the reflectivity function and input pulse. Our primary objective is to recover to know the reflectivity function based on the output seismic trace. So my next slide. So this is the seismogram, reflectivity function, and WT is the input waveform plus noise. So as I am telling, what is the main application of the autocorrelation function and how do you recover the reflectivity function source wavelength? So we know if we convert the reflectivity function with the source wavelength, we will get a seismogram. Generally, it is our assumption that the reflectivity function is random. We assume, and when the reflectivity function is random, the autocorrelation of that will produce the Dirac delta function. So when you convert the Dirac delta function with the autocorrelation of the wavelet, it will produce the autocorrelation function of the seismogram, and the autocorrelation function of the output seismogram is exactly same as the autocorrelation function of the input wavelet. So seeing the autocorrelation function of the seismogram, we can define how is the initial wavelet is there. We can have assumption, but the in reality the autocorrelation function of the seismogram is not equal to the Dirac delta function. So in that case, only the initial parts of the autocorrelation of the seismogram, it is having the same characteristics of the autocorrelation of the source wavelet. Okay, so you see that the seismic trace is the convolution operation, and generally this source wavelet, that is called the minimum phase pulse, that is generally used. All the energies are concentrated at time t is equal to 0 position. This is called the minimum phase pulse. What I have today covered, very important topics you must have followed and you should know. I mean, these are fundamentals of the seismic method, the signal system, the sampling theorem, the aliasing, Fourier transformation, waveforms, box function, unit step function, uh, and mainly the CDP, data acquisition, sources of energy, and the digital recording, and the different types of multiple, and very importantly NMO correction for the seismic processing. So the seismic main interpretation I will be describing in further my next lecture. Hope from my this lecture you will have a feelings of mathematical and the physical feelings, so that you can easily apply on this exam. And if you have any, let me know, and don't forget to like, share, and comment on my channel, and always turn on the bell notification icon to get further more updates for your benefit. So this is my channel, Physics and Geophysics Learning. Thank you very much.